Ready? Okay. So, okay. Good afternoon, all the participants. So before I actually start this lecture, I thought I will show you this textbook, which I have published recently. So this might be helpful because I am going to use much of the material from this book. So you might be able to follow it better if you have this copy or download it, or I don't know if you can download it or not. But the title here actually tells you everything about what it contains. So you can see here it begins with the FID on the top here. This is the FID, and then your Fourier transformation, you get the spectrum, and then you have the magnet here in the middle. So this was superconducting magnet. So all the technology is described there. Then you have this analysis of the spectra here. The Hamiltonian is given, analysis of spectra of 2 spin, 3 spins, all various kinds of combinations. And a more complicated analysis using the density operator that is here. This is the equation of the density operator. It's called the Liouville equation. And the solution of that is also given. What is the solution of the density operator, the density matrix? And this is what is used for analysis of all complex NMR spectra, multidimensional NMR spectra. And then we have this 2-dimensional spectroscopy here at this point and 3-dimensional spectroscopy at this point. So these are contained in different chapters in the book. So you might be better off and getting access to this book if it is possible for you. Okay. So from here we will continue, and the next few lectures is going to be fair amount of well, I'll try to minimize as much as possible. Some amount of mathematics is required. Some principles, wherever it is necessary, I will try and explain the ground principles over there. Okay. So next. Okay. Just a recap of what you might already have seen in previous lectures. There is the first thing about the FTNMR spectrum. FTNMR actually laid the foundation for all the later developments, including multidimensional NMR spectroscopy. And here you have the basic concepts. You have the FID. FID, if it is a cosine function here, as it is indicated here, and then the function, the FID decays by this factor e to the minus at multiplied. And then if you have an FID like this, it gives you a spectrum which is like this. This is absorptive signal, which is already written there, absorptive signal. Notice here the FID starts with the maximum value here, starts at the point 0, it has maximum value, and it decays with time. This is called the cosine form of FID. Cosine omega at to the minus at if we have it, and there will be a cosine Fourier transformation. It is also often called as real Fourier transformation. You will get a signal which is absorptive in shape. If on the other hand, if your FID starts with 0, as it is here, the sine function starts at 0. Sine t at t is equal to 0, sine function is 0. So then it starts oscillating in this manner and decays with the same time constant. And then if you do a cosine ft of that one, it will give you a dispersive signal which is looking like this. The integral of this dispersive signal is 0. The integral of this absorptive signal is maximum. And that comes from the basic theorems of Fourier transforms. Okay. To give a little bit of a relationship with respect to the phase of the RF and the phase of the FID and then the signal phase. So these are contained in this. There are 3 situations I have considered here. You apply the pulse, 90-degree pulse along the minus x-axis. The FID, the magnetization rotates onto the y-axis. If you apply a 90-degree pulse along the y-axis, the magnetization rotates onto the x-axis. If you apply 90x pulse, then the magnetization rotates onto the minus y-axis. So these are 3 different situations I have considered. You can also have in-between things. Okay. What happens, and if you are collecting the FID, you are detecting the y magnetization. The detector is kept along the y-axis. Okay. In this situation, what do these different excitations result in the FID form? For example, in this situation, the FID phase, we say this is the f of t, this is the f of t, the FID. It starts with maximum and then goes in this manner, decreases, decays in this manner. In the second case, the FID starts with 0 because you see that at time point t is equal to 0, it is 0. The value is 0. It is a sine function. The sine decaying function, it will produce a FID of this type. Okay. And the third one is then now the magnetization is along the minus y-axis. Therefore, it starts here. The first one, the FID starts here. The third one, the FID, initially the magnetization is oriented along the minus y-axis. Therefore, it starts with the minus value. Starts with the minus value and goes up and then comes down and it decays. What does it mean in terms of the spectrum? So you look at, this is the FID phase, okay? The signal phase, in the first case, you get an absorptive positive signal. I've written here F0 greater than 0, F of 0 greater than 0. Notice here the relationship between the FID and the frequency domain. This is the Fourier relationship here. So F of 0 means the first point in the FID, that is F of 0. That is the integral FW, F omega d omega. That means it is the entire area under the spectrum. So F omega d omega, that integral of that one is equal to F of 0. That means the first point in the FID contains the entire information about the spectrum. It is the integral, complete integral. So therefore here you see the first point in the FID in the case here, in this case, it is maximum. And assuming you are considering one line here, therefore if there are more lines, it will be the integral of all of those. Considering one line FID, then it will be a signal which is absorptive and positive because F0 is greater than 0. It is positive. Now the second case, F of 0 is equal to 0. Okay, this is the sine function. When we have the sine function as the FID decaying, now F of 0 is equal to 0. Therefore, the integral of this spectrum has to be 0. That already indicates to you that this is the dispersive signal. This also I mentioned to you in the previous slide. When you have it originating from the sine function, that the starting point is 0, it will produce you a
just make it Latin.
So F of 0 is equal to 0, then it will give you a dispersive signal. Okay, but intuitively you can see this. Because at time point t is equal to 0, if the integral is 0, the integral of the spectrum has to be 0. This means in a one line case, it will be a dispersive signal. It will be the same for many line signals also. And in the third case, the F of 0 is negative maximum. Therefore, the signal is also negative. Okay, F of 0 is less than 0. Therefore, the signal is also negative. These are important because this will determine the line shape in your spectra. Finally, if there is a mixture of this and this, sometimes it can happen, then you will have phase errors, and then of course you will have to do phase corrections and things like that. These are all situations when there are no phase errors, data is collected in a pure form, and there are no errors with regard to the pulsing, with regard to the detection, everything, then you will have all these clean phases in your spectrum. It can be positive, signal can be negative, or it can be dispersive, or it can be absorptive. All these situations can arise, and you will see that's why various kinds of line shapes in your spectrum. These I'm bringing it back to you here, although you might have seen this in the previous lectures, but these are going to be important in two-dimensional NMR spectra also. There you'll have to apply these along both the dimensions, not one dimension, which we are going to discuss soon. Okay, so this is the background for the Fourier transformation. The theorems of Fourier transform are the same whether it is one-dimensional spectroscopy or two-dimensional spectroscopy or three-dimensional spectroscopy, whatever it is, the theorems are the same and the principles are the same. Whatever. Okay, so now we enter into this topic of multidimensional NMR spectroscopy. To begin with, we will use two-dimensional NMR. Of course, it can be extended into the multi-dimensions. The fundamental principle here is what is known as the segmentation of the time axis, which I already previously mentioned to you. When you do Fourier transform NMR, the excitation and the detection are separated in time. Excitation is by the 90-degree pulse or whatever pulse you apply. When you are actually detecting it, there is no perturbation. It is a free precession. That's why this FID is called as the free induction decay. There is no perturbation, and you collect the signal as the signals are, the spins are precessing without any perturbation. That's why it's called free precession. And the signal decays because of the relaxation times, and therefore it is called as the FID, free induction decay. Now, two-dimensional NMR is an extension of that. You segment the time axis, and you can introduce various kinds of perturbations in between before you detect it. You excite the system here during the preparation. Preparation can be one pulse, or it can be a series of pulses, or it can be anything else also. Okay, and then you have a period called as evolution period. What they mean, I will explain to you very soon. there is a certain period called evolution period, and this will label as T1. And then there is a period called as mixing period, which actually is the crucial thing for giving various kinds of information in the two-dimensional spectrum. And the detection is your usual FID. This is your usual FID, which you delect in your Fourier transform ANOVA spectrum. So this is where you collect the FID. Now, the preparation determines the initial state of the spin system before excitation. Okay, and you can do it, various kinds of preparations you can do, prepare the system in a particular way you want, and then you can monitor this as through the experimental sequence. Mixing is based on interactions between the spins. This causes transfer of information from T1 to T2 time periods. That's why it is called as mixing. It mixes the information between the various spins and transfers information from one time period to the another time period. Okay, data is collected explicitly during the T2 period only, and that is our FID. Okay, so now T1 I have labeled it as T2 is one which are a large number of time points, right? You have seen the detection period, you collect 1024 points or 2048 points and things like that. Whereas T1 is one time point. So now for every T1 value, you collect 2048 or 4096 points. So what the T1 value means that you keep on incrementing that. You keep incrementing the T1 period. So you generate a whole number of experiments with the incremented T1 values. That is how you generate an independent time variable, which is called as T1. Therefore, you can generate a two-dimensional data matrix by having independent time variables T1 and T2. This is explicitly shown here. The experimental protocol, you have the preparation. In the first time point, the T1 is equal to 0. Ideally, of course, you will have certain time small gap of 100 or 100 nanoseconds or something like that before the preparation and the mixing. Schematically, it is shown how the experiment is performed. Then you increment the value of T1 by delta T1. So you keep collecting FIDs, various FIDs. You do the third experiment, 2 times delta T1, the increment, the third FID, the 3 times delta T1, fourth FID, then you have 4 times delta T1, fifth FID, and so on. This you can go on for, let us say, 256, 512, or 1024 time points. So you generated 1024 time points along the T1 axis. There is almost like generating another time variable. So you get 2 time variables. T2 is a time variable which contains the FID is collected in about, let us say, 2K points or 4K points, right? Usually in all of these, FID contains 2K or 4K points. It is up to you. It depends on how much space you have on your disk and how much time you want to give. You can collect various number of data points. This will remain the same for all the experiments. But the T1 is incremented systematically, one by one, you will have to keep incrementing that. Therefore, the total number of machine experimental time will be dependent on how many T1 values you use. Okay, that determines the experimental protocol for the two-dimensional spectrum. Okay, how does it look like? This is again a schematic. How does the two-dimensional experiment work? Consider here these many experiments performed. First of all, you have the time T1 is equal to 0. You have the FID, which is like this. And as we said before, it produces a spectrum, which is like this. Absorptive spectrum. The second one, the magnetization. So assuming that you have created a certain evolution of the magnetization and your FID does not start from the maximum, but it starts with a slightly lower value. Okay, so your FID is starting, in the first case, it is starting like this. In the second case, it is starting somewhere like this. Okay, it is a lower value because the magnetization is evolved during this time period. And during the time period, the component which you are actually measuring along the y-axis, let us say, the y component might have reduced. I will show you here a schematic. So if this is your initial time point, t is equal to 0, t1 is equal to 0. During the second time point, this has the magnetization may have moved here. If it has moved here, this component is reduced. Okay, if this component is reduced, its initial value will be smaller. And therefore, the initial value at this particular, and this is the evolution that has happened during the delta T1 period. Okay, so it starts at a slightly lower value, but it continues in that manner. And therefore, you will see this spectrum has a lower amplitude compared to this, lower intensity compared to this. You may have a third one where it comes down to 0, the fourth one which has gone to the negative value, the fifth one negative value increased, sixth one negative value further decreased, and then again 0, again this, like this. So you see your FID, the spectrum also keeps changing, appearance of the spectrum changes as you increment the T1 values systematically. Okay, in this case, these are all absolute value spectra. These are not phase sensitive spectra, but it doesn't matter. It gives you the concepts clearly. Now you have here various spectra. Let us look at this is the spectrum here F2 after Fourier. What you get here is this is the FT. This is after the FT, the first FT here. Okay, after the FT you are getting this. Now this, therefore, this is what I collected the data F2 Fourier transformation gives you the F2 domain spectrum. The time frequency axis is T2. Now look at the different points here, A, B, C, D, E, F, G. Consider these various points and you look at each of these points on the different spectra here. Okay, and you plot them here. You plot these, the values of at the points in the spectra at value A, at this point, this point, this point, this point, this point, like this, all of them, you plot them here. So this generates a time variable here, because what is varying here? This is T1, right? That's what is written here, down here. That is T1. So as a function of T1, this is how this point A is varying. Come to B, you see there is a small dip. Here it is 0. At this point, there is a dip here. At this point, there is a dip. Somewhere, if you go, this point is here. B, like this. You took at this, the various points here. There is a small dip here. So which gives you a small signal of this type. You take the point C, which is one close to this. This is a very high signal at this point. Therefore, it shows a much larger dip here. The intensity of this point is large. Therefore, it shows that variation. It shows also variation because of the value is not the same in all the spectra. So you get, now if you do a Fourier transformation along this again, what is this Fourier transformation? This is the second Fourier transformation. The second Fourier transformation along the T1 dimension. So your time variable is now T1. If you do this variation, you get this. So these points will be, again, you see there is this is an FID here, and this is a frequency domain spectrum along the F1 dimension. So this is how you generate two independent time variables. Various points you collect, FIDs you collect at different intervals of time, systematically incremented time values, T1s, and do the Fourier transformation and look at the individual spectra as a function of T1 value. This is plotted here. Now, therefore, it again generates another FID, and you Fourier transform that along that axis, you generate a spectrum again. Okay, so therefore, this is a schematic of the two-dimensional data collection. Okay, this is a mathematical representation of that. A two-dimensional frequency spectrum will be generated from a two-dimensional time domain data set, S, T1, T2, by two-dimensional Fourier transformation. Mathematically, this is represented as S, F1, F2. This F is a Fourier transformation operator. This operates on the time domain signal S, T1, T2. This can be broken up into two operators. One is the Fourier transformation along the T2 domain, and the other one is the Fourier transformation along the T1 domain. And then along the T1, T2 dimensions, so these have to be carried out independently. Notice here, it does not matter which one you do first. After you collect the two-dimensional data body, it does not matter whether you do F1 first or F2 first. It doesn't matter at all. You can, but more conveniently or conventionally, it is easy to understand if you do F2 first and then the F1 second time. This is what I showed you schematically in the previous slide. Okay, so this is the same thing represented here. To consider a spin K whose XY magnetization has been created by the preparation period. This magnetization evolves. Now I am drawing here. This is the K spin. Magnetization has been, this is the XY plane. Okay, let us say this is the Y axis and this is the X axis. We have created a magnetization here. Okay, so consider the spin K whose magnetization has been created by the preparation period, and this magnetization evolves with the frequency omega k. Now this moves, magnetization moves here, right, with the frequency omega k, because this belongs to the spin K and its frequency of precession is cosine omega k, and this will evolve with time during the period T1. So at the end of the T1 period, the magnetization has components MK0, what is MK0? MK0 is the value at this point, is the value at time t is equal to 0. And it has moved to this point here, let's say, then it has a cosine component and a sine component here. Sine component, right? So therefore, cosine component is MK0 cosine omega k t1 and MK0 sine omega k t1 along the y and the x axis respectively. Okay, I've written MK0 is the mechanization and the beginning of the evolution period. Now let us now assume that the mixing period transfers part of this mechanization to spin L. So far it is K spin. Now the mixing period comes. At the end of the T1 period, this is what the mechanization condition is of the K spin. Now the next is the mixing. What does the mixing do? Mixing transfers part of this mechanization to the L spin. This we said mixing does that job. This can be one pulse or many pulses or whatever. And it is a transfer of perturbation. It transfers part of it to L spin. Then what you get, there will be, some of it remains with the K spin, some of it goes to the L spin. So therefore, when I connect the time data, the data along the T2 axis, detected signal as a function of T2 will then have two contributions. Which are these two? A and B. A is MK0 cosine omega k T1 cosine omega k T2, because whatever remained with K evolves with the frequency omega K. And let us say that fraction is small a. That fraction is small a. So therefore, this mechanization represents whatever remained on the K spin by the mixing also. Then this represents the part which has been transferred to the L spin. So during the T1 period, this mechanization was cosine omega k T1, MK0 cosine omega k T1. But now, as a result of mixing, this has moved to the L spin. Now the L spin will evolve during T2 with its own frequency, that is omega L, right? So therefore, during the T2 period, it goes with its characteristic frequency omega L. Therefore, this mechanization there, the B term will be cosine omega k T1 into cosine omega L T2. Okay. Now, if I Fourier transform this, if I do a two-dimensional Fourier transformation here, what are the frequencies? What is the frequency in the F1 period? F1 period, the frequency is omega k, and the F2 period is also omega k. Therefore, this will appear as a diagonal peak. If I make a thing here, this is F2, this is F1, and this is omega k, and this is omega L, let us say. Okay, so this point, you see, the A term gives you the diagonal peak. It gives you a peak here because it is the same frequency along both frequency axes. The B term, it has omega k at this point, but the T2 period, it has a frequency omega L. Therefore, it produces a peak here. Okay, so if I do two-dimensional Fourier transformation, this will produce two peaks. One is the one which is at omega k, and the other one will be at omega L. And that is how you get what is called as the cross peak. What is present at the same frequency is the diagonal peak, and what is present at another frequency is called as the cross peak. So here it is assumed that only the y component of the magnet is detected during T2 period. A and B are some coefficients representing the relative contributions. These equations represent, of course, oversimplification made to convey the concepts. I mean, we have assumed many things here, that we have done a y magnetization, we have done cosine transformation, but that doesn't matter. All of these things apply even when you do the complex Fourier transformations or sine transformations also. But this makes the ideas, concepts clear. Okay, so this is schematically shown here. So a two-dimensional spectrum which I showed you here. So you have two frequencies, omega k, omega L, and they have the two on the diagonal you have the two peaks. This whatever originated from omega k, part of it remained as omega k, that caused the diagonal peak. Whatever got transferred to omega L came as a cross peak. Similar thing will happen to omega L also. Suppose during the T1 period you had the omega L frequency. At the time of the mixing, part of it gets transferred to omega k. Therefore, you will also get this peak. This, therefore, if there is a symmetry, you get two cross peaks and two diagonal peaks. This is called the typical correlation spectrum, typical two-dimensional correlation spectrum. And schematically, one can show like this. There is much more complex situation that we will analyze that in greater detail. So this is called as correlated spectroscopy in general, but the correlations can arise as a result of different kinds of mixing. The mixing is the crucial period which determines what sort of a magnetization, what sort of a transfer will happen, and that determines the nature of the spectrum. Okay, so in each of these cases, what will be the line shapes? There can be different line shapes. Now we are talking about two line shapes. One is the line shape along the F2 axis, other one is the line shape along the F1 axis. Now, if we have the same line shape along both axes, along both F2 and F1, then you get a peak pattern like this. Absorptive along both axes. Because you see, this is the contour representation of this peak here. So you take projections at various places, the cross sections at various places, plot them as contours. So this is the contour representation of your peak. Now, no matter what cross section you take, see, it has an absorptive line shape. Whether you take a cross section like this or a cross section like this, you get an absorptive peak. And this other one here, the C part which is here. Now, if you take cross sections here, this is dispersive along both frequency axes. Therefore, you see here, along no matter where you take the cross section, whether you take a cross section like this or a cross section like this, you get a dispersive line shape. The dispersive line shape, remember, is like this. Along both axes, you have the dispersive line shape. The third situation is you have absorptive line shape along one axis and the dispersive line shape along the other axis. So here you have along the F2 axis, you have the absorptive line shape, and the F1 axis, you have the dispersive line shape. These lead to what are called as mixed phases, and that then leads to very complex spectra. It can lead to a lot of loss of resolution in your spectra, and we should try to avoid this. As much as possible, one would like to get this kind of a peaks, and it will improve the resolution in your spectrum. Clear identification can be made if you have line shapes of this type. Okay, now there are different kinds of 2D spectrum. The known 2D NMR spectrometers can be broadly classified into three categories: the resolution and separation experiments, correlation experiments, and multiple quantum experiments. By and large, the most popular ones are the first two, resolution and separation experiments and the correlation experiments. Multiple quantum experiments are used in some situations. Remember, I'm not talking about multiple quantum filtered experiments, though they're different category. The correlation experiments can have multiple quantum filters. That is a different matter. But multiple quantum experiments, meaning on one axis, you have the multiple quantum signals themselves. Okay. Multiple quantum is double quantum or zero quantum or triple quantum. You can have them along one of the frequency axis. But those ones are not as much used in general, where as much as the resolution and the correlation experiments. Okay, we will try and understand this from the first principles as much as we can. Somewhere we will have to go a little bit more theoretical, and that becomes in the case of correlation experiments. Resolution experiments, we will try and understand it in a simple manner now. Okay, first category, 2D resolution experiments or separation experiments. What is the meaning of separation here? So I use separation experiments. Okay, the primary aim in these experiments is to separate the different interactions in the Hamiltonian. The Hamiltonian is the one which actually describes the different interactions, right? So we have already described in the previous classes that you have the interaction with the magnetic field, which is called as the Zeeman interaction, and then you have the spin-spin coupling interaction, which is the J interaction, J coupling interaction. Therefore, typically you have two components in the Hamiltonian. And this is the HZ, this is the so-called Zeeman interaction, and HJ is the spin-spin interactions. Typically in high resolution NMR, you have only these two. If you go to solid state NMR or other kinds of NMR, then you will have another term which is called as the HD, which is the dipolar interaction. The dipolar interaction gets averaged out in solution phase, therefore we do not consider that at this moment. When the solid state NMR is discussed, at that time the HD is included. But HD, the dipolar Hamiltonian, does become important in the case of NOE. NOE, the dipolar interaction plays a crucial role. And we already seen that when you describe the NOE, dipolar interaction mediated transfer of magnetization. So different strategies can be defined depending upon the nature of the information required in the final spectrum. Okay, let us see some examples. Okay, the first example. Typically, what we have here, we have considered a heteronuclear experiment carbon 13 measurement. Carbon 13 measurement, you have you have two channels. Therefore, heteronuclear experiments mean you have two channels, the carbon channel and a proton channel. So we start with in the carbon channel, we apply a 90-degree X pulse. So therefore, which means we create a transverse magnetization of carbon, which may be along the y-axis or the minus y-axis. Then you have the T1 period, the evolution period. Then you are actually detecting the signals T2, you decouple the protons. During the T1 period, you are not decoupling. During the T2 period, you are decoupling. So therefore, what I should have during the T1 period? I should have both the chemical shift information as well as the coupling information. And during the T2 period, I must have only the chemical shift information. Okay, so here is a schematic of that sort of a situation there. You consider a carbon spectrum which has a triplet, one triplet here. So this is along the F1 axis. This is the triplet here, a carbon spectrum which is a triplet. Then I also have a doublet. Then I have here a quartet. Then I have a triplet. Okay, so this is my carbon spectrum. Carbon spectrum, coupled carbon spectrum has these many things. Now, the diagonal, as I said, represents the chemical shifts. So therefore, at this point, you look at this point here, this is the diagonal point, middle of the diagonal points. Therefore, that is the chemical shift of the particular nucleus, is the chemical shift of this. And the center point here is the chemical shift here. The center point here is the chemical shift here. The center point here is the chemical shift here. Okay, and therefore these appear at different points on the diagonal. Now, this is the F1 axis. Remember, this side is the F1 axis. F1 axis, I have the coupling. I have the coupling information. Therefore, I have three peaks here. So there the chemical shift is this point and the triplet here because of the three peak. The coupling is present. This fellow has only a doublet. The chemical shift is at the center and there is a doublet. And this one is a quartet. You have the chemical shift at this point and the multiplicity as in this four peaks. And similarly, you have the triplet here. Okay. So in this case, therefore, in the T1 dimension, I have both the chemical shift and the coupling constants. And the T2 dimension, I only have the chemical shift. So suppose I were to take the projection here, what will I get? I will get one line here, one line here, one line here, and one line there. That is the F2 spectrum. F2 spectrum is therefore chemical shift information only, right? Therefore, I have decoupled the carbon. I have decoupled the proton. Therefore, along the F2 axis, I will only have the carbon chemical shift. I can do the experiment in the reverse way as well. Okay. So if this is clear, then let us see how we can manipulate. We can go to the reverse way. I do the experiment in the reverse way as well. If I do the experiment in the reverse way, what do I get now? The pulse sequence remains the same, except I shift the decoupler. I shift the decoupler to the T1 period. So during the T1 period, I decouple, but the T2 period, I have both frequency axes. So during the T2 period, I have chemical shift as well as the coupling. Therefore, that whole pattern gets rotated. Whole gets pattern rotated. The chemical shift is at this point. Chemical shift is at this point, but the coupling will now appear along this axis, along the F2 axis. For the F2 axis, I have the coupling. F1 axis, I don't have the coupling. Therefore, F1 axis, I have one line here, one line there, one line here, and one line there. There is only chemical shift. Along the F2 axis, I have both the chemical shift here, and the splitting there. The triplet, quartet, doublet, and triplet. So therefore, you can see how you can manipulate your appearance of the spectrum by designing appropriate pulse sequences. And what we have achieved here, in this process, we have achieved separation of the chemical shift and the coupling constant. That is why it is called as a separation experiment. The chemical shift is along one axis only. Therefore, here I have only the chemical shift information, Hz. Okay. And along this axis, I have the chemical shift plus coupling. Okay, so one portion of the Hamiltonian is kept along one of the axes. Okay, so this, let me write it properly. Okay, so along one axis, I have only the Z1 interaction. On the other axis, I have both Z1 plus J interaction. Okay. Now, can I do better than this? Yes, I will show you some practical example here. This is the chemical shift. This was the first ever experiment performed. Okay, you can see that Anil Kumar is involved in that. He was the one who was there with Richard Ernst as a postdoc at that time, and they recorded this spectrum on a simple molecule which is indicated there. What do you see here? This is the F2 axis, omega 2 is the same as the F2, and this is omega 1 is the same as the F1. And now you see along the F1 axis, I have the coupling as well as the chemical shift. Along the F2 axis, I only have the chemical shift, single lines. Check the projection there. Now, if you took a projection of all of these, look at the spectrum, how it looks. Complex. You can't analyze this, right? So now, by doing this experiment, you got this separated out on this, and therefore this allows you to identify the multiplets. The quartet is clearly seen here. The triplet is clearly seen here. The triplet is clearly seen here. When you roll superimposed, this is the normal one-dimensional spectrum, carbon-proton coupled spectrum. In this, you will not be able to see. You cannot see them, right? Therefore, when you did a two-dimensional experiment, the two interactions got separated out, and you are now able to see the quartets, the triplets of this molecule very clearly. And you can see this is a very simple molecule, simple hydrocarbon, and you have this spectrum recorded. And this was the first ever, therefore I show this everywhere, wherever we have to give 2D NMR spectra. So this is the first spectrum ever recorded. Okay, so now let's go to a little bit more complex situation, and this is the heteronuclear spin echo. Okay, so what we have here, we use the spin echo. So again, we collect in the carbon data. The carbon data is along the, therefore one axis, one channel you have the carbon, other channel you have the proton. And this is my spin echo. From here to here, it is a spin echo, right? 90, 180, 90 T1 by 2, 180 tau. See, what we have done is simply in the previous case, instead of, there was no 180-degree pulse, we simply had the 90 and the T2 period and the decoupler. This was the simple experiment earlier. There was the first experiment which I showed you, and that is this one. This one. Now what you do is, in the T1 middle, the middle of the T1 period, I put a pair of 180-degree pulses. So therefore, now this becomes a spin echo. As a result of this, what we have achieved is during the T1 period, there is no chemical shift evolution, because the spin echo refocuses the chemical shifts. For all the carbons, the chemical shift is refocused. So what is present? Since I have applied a 180 pulse on both of the dimensions, on the both carbon and proton, the coupling information is retained. Therefore, during the T1 period, the coupling information is present. And therefore, the chemical shift is zero. Right? All of them are refocused. I lost that chemical shift information. And along the T2 dimension, what I have? T2 dimension, I have only the chemical shift, because the decoupler is on. The decoupler means I remove the coupling. Therefore, I only have the chemical shift. Now you see, during the T1 period, I have only the coupling constant, and the T2 period, I have only the chemical shift. A complete separation of the two interactions. Complete separation of the Zeeman Hamiltonian and the J coupling Hamiltonian. So this is eventually represented schematically like this. Therefore, along the F1 axis, since there is no chemical shift, it is zero for all of them. So I put it on one horizontal line, it is the chemical shift for all of them, that is zero. Along the F1 dimension, I only have the coupling constant. Therefore, a triplet will appear as a triplet, and quartet will appear as a quartet, doublet will appear as a doublet. Therefore, along this, I have the triplet here, a quartet here, and a doublet there. And here I have one line. If I take the projection here, one line here, so one line here, the projection here. So this is a fully decoupled homonuclear spectrum. It's not easy to obtain. A fully decoupled homonuclear spectrum is not easy to obtain. Typically, in decoupling experiments, you irradiate one particular proton, and that carbon will get decoupled. But in this situation, you see, we have obtained a completely decoupled, homo-decoupled carbon spectrum here. one experiment. This is not broadband decoupling. This is a two-dimensional version of the experiment. In this two-dimensional version of the experiment, I have also the completely decoupled spectrum, but I have not lost this coupling information. The coupling information is present along this axis. Therefore, you identify the carbon, you also identify what sort of a carbon it is. This is the CH2 carbon, this is the CH carbon, and this is the CH3 carbon. Okay, so therefore, this is an extremely useful experiment, heteronuclear spin echo. Okay, I think that's the end of this thing, and we go to the next one.
Okay, sir, you can take
You
a.
can take a break here.
Yeah,
Let's take a 10 minutes break.
Yeah. Students, you can ask if.
Any questions if you have, we can go back and look at this. If there are any questions unclear, we can see. Take that up.
So there is a
There is a question? Yeah.
why FID should be seen only in the T2 times scale. So there is a question at
Where?
the bottom.
Radharaman Samant.
Why FYD should be seen only in T2 time scale? Oh, you have the receiver during the T1 period, you are allowing the system to evolve and you transfer the information from the T1 period to the T2 period and you collect the data in the T2 period. You have not lost any information. By doing a two-dimensional Fourier transformation, whatever is information is present in T1, you are recovering it because the T2 data gets modulated by the evolution during the T1. Therefore, the information is already present in the collected data. So it is adequate to collect the data with one receiver as a function of T2, but that various FIDs are modulated by the evolution of the spin system during the T1 period. So information is transferred from the T1 period to the T2 period, and therefore you don't need to have another detector over there. You don't need to collect explicitly the data. Otherwise, it will be like a one-dimensional spectrum. Yeah, any other question?
No question.
Okay, that's short break, then we'll
Okay.
start.
Yeah, we'll have a short break for
Sir, when you
the spin echo does not refocus the coupling evolution. See the carbon, when you apply the 90-degree pulse on the carbon, you create a transverse magnetization of carbon.
Yeah.
The carbon is now evolving under both
Okay.
chemical shift and coupling constant.
Okay, and then you are now
Removing the
Okay.
chemical shift.
Yes, now it is clear.
So the coupling is
Yeah.
not removed.
So the first T1/2
Yes.
is you are allowing to this the coupling information to
Go on. During the next T1.5 also it will go on.
Yeah.
So in the entire sequence, the chemical shift of the carbon is refocused
Yes.
because the carbon evolves under both the Hamiltonians,
Right.
proton, the HZ and HJ.
Right.
HZ is getting refocused because of the spin echo,
Yeah.
but HJ is not refocused
Yes.
since I am applying pulse on both.
Okay. Yes.
That is a spin echo. That is what happens in the case of a spin echo. So this we did in the last class. We explained that how it happens.
Right. Now it's clear.
Yeah. Okay, now so far we used hand waving arguments and vector pictures, vector diagrams to describe the magnetizations and transfers wherever possible. We could explain that. But there is a limit to what we can learn from there, how much we can learn. There is everything that happens in correlated spectroscopy or multiple quantum spectroscopy cannot be understood by the vector picture. So these are much more complex, and therefore one has to adopt a much more rigorous treatment, and that is called as the density matrix description of NMR. Now we are taking a slight diversion because we are going to go into the theory of these representations, and we will come back to the discussion about the various multidimensional NMR experiments after this, because otherwise we will not be able to appreciate and understand that. Therefore, we have to make a small diversion here to describe the spins, the theory of the NMR in a little bit more detail. And this is called as the density matrix description of NMR. What is density matrix? Let's start from there. Consider that I have a spin system with these many energy levels. All these black bars here, these are the energy levels. Okay, and each one of them has a population Pi and an energy EI. Okay, I is the label of the level. So it can go from I, J, K, L, whatever there is level. So this is I. All these levels are indicated simply by the index I. Okay, and there can be various kinds of transitions between them, correlation between these levels, and these are indicated by these blue arrows. The system can be in an equilibrium state or it can be in a non-equilibrium state. What does it mean, equilibrium state? Equilibrium state means that you have all the populations as per the Boltzmann statistics, because we follow Boltzmann statistics for the nuclear spins. A non-equilibrium state can mean the populations are not in equilibrium. This is what we saw in the case of NOE. When we described the NOE, populations were not in equilibrium. We perturbed the populations, increase the population somewhere, decrease the population somewhere, and the interactions caused the transfer of information from one spin to another spin. And that was an example of the non-equilibrium state operation in the NOE. We could explain that by populations alone. But there are also certain other things which are called as the coherences, the phase coherences. The spins in this level and the spins in this level may have a phase coherence. They may be evolving with a certain phase coherence, and then it leads to what is called as a transition. Single quantums can lead to transitions, and the other can be multiple quantum transitions. These are multiple quantum coherences which can happen. Okay, to give a certain little bit explicit example, the density matrix in the most general form is represented in this manner. We will not go into the derivation of this. I'm giving the final result. There is a derivation as to how this will come, but we will not go into that. I'm giving the final result of how the density operator, density matrix looks like. Density matrix, you suppose you have a n level system. In the previous case, we had indicated the levels. Suppose there are n levels. Okay. What you do is each n level has a population. So you put this populations along the diagonal of this matrix. So you have the P1, P2, P3, P4, Pn. You have all the populations are put along the diagonal. And then you have the various kinds of phase coherences between the energy levels. So you have the state 1 and 2, 1, 3, 1, 4, 1, 5, 1, n. So you have the coherences between the spins in these individual states. How does this coherences arise? The creation of a transverse magnetization is an indication of the coherence, the phase coherence between the spins. Okay, so therefore these ones are the coherences. These ones are the coherences there. This is the magnitude of the coherence, and these ones will evolve with the time because we have a time dependence here. See, the coherences evolve with the time. So what is the meaning of coherence? To give a simple example with the two spin system with a single two levels. Suppose there is a magnetization here. This magnetization rotates here, right, with the time. So this is the rotation. This evolves with the time. We wrote the cosine omega kt1, sine omega kt1, etc. So that is the phase coherence, the transition in the case of single quantum transitions, that is a rotation, that is evolution in time. This is what we are trying to say. The system magnetization evolves in time, and that's how you get this cosine terms and sine terms. We will see that explicitly also here. This is the more generalized representation of that. Coherence between the state 1 and 2 is represented by this. Coherence between the states 1 and 3 is represented by this. The phase coherence between the states 1 and n is represented by this. Similarly, you have the between 2 and 1, 2 is the diagonal, 2, 3, 2, 4, and 2n. So like that, n1, n2, n3, and finally population. Nn is the population. Nn is the same state. So therefore, that is the population. So you have the populations along this axis, along the diagonal, and how many coherences will be there? If there are n states, the total number of coherences can be n into n minus 1 divided by 2. Because n square is the total size of this. How many elements are there in the matrix? N square matrix, n square elements. N square elements, so remove the diagonal element, there are n diagonal elements, so n square minus n, and you have on the top half of them and the bottom half of them. So n into n square minus n, half of that will be on the top portion of the diagonal and the other half will be in the bottom portion of the diagonal. Basically, this is the complex conjugate here. You notice here omega 21. What is the definition of omega 21? Omega ij is defined as 2 pi ei minus ej divided by h. And ei minus ej is what? Ei's are the energies of the state. Ei is the energy of the state I, ej is the energy of the state j, and ei minus ej is the energy difference between the two states. And 2 pi by and divided by h, it gives me the nu, that is h nu. E is equal to h nu, right? This formula you know, E is equal to h nu. So if I divide it by h, I get the nu, and 2 pi times nu is the omega, that is the angular frequency. So therefore, these coherences are angular frequencies. Angular frequencies, these represent the evolutions of the spins in the individual states. If they are evolving with a certain phase, that phase appearance, it will not stay stable because it will also decay because the two energies are different. Since they are evolving with the different energies, so the system will evolve with the e to the IET. Each level, the spin, you will evolve with the e to the each state e to the IET. This is how the phase will go for each state. And the second state, will be e to the suppose I call it as EIT, and the other one will be e to the IEJT. And are these going to the same? They are not the same. So since EI and EJ are different, there is going to be difference in the phase. So how this phase changes with the time? If I take the phase difference between these two spins, the difference will be e to the IET and the EI minus EJ times t. That will be the phase difference between the two spins evolving in the two states. Okay, so that is why we said, so this is the evolution of the phase difference between the two states 1 and 2. And this is the evolution of the phase difference between the states 1 and 3. And likewise, so you have these many combinations. For every two levels, there is a phase relationship between the spins evolving in those ones. The phase evolution happens by this, e to the IET. This comes from the time-dependent Schrodinger equation. So you have the evolution of the spins in the individual states. Okay, so therefore, the density matrix in the most general case is represented in this manner. Okay, now in equilibrium, when the system is at equilibrium, all the spins are in equilibrium. When there is equilibrium, there is no phase relationship between the individual states. So in that situation, what will happen is all the diagonal elements will be populations only, and all the off-diagonal elements will be 0 because there are no phase coherences. Diagonal elements represent populations and off-diagonal elements represent phase coherences between energy levels. Cij represent the extent of phase coherence at time t is equal to 0. The coherences evolve with the time. Okay. So at equilibrium, next slide shows a little bit more explicit situation there. For a two-spin case, that was a generalized case. Here I have only two spins. In the two spins case system AX, how many energy levels are there? There are 4. 4 energy levels. I represent this as alpha A, alpha X, beta A, alpha X, alpha A, beta X, and beta A, beta X. These are the 4 energy levels. This we all know. Okay. Now, and what is, we also know that 1 to 2, this is a transition, single quantum transition. 1 to 3 is also a single quantum transition. 2 to 4 is a single quantum transition. 3 to 4 is also a single quantum transition. These are also called as coherences. Okay, single quantum coherences are the same as single quantum transitions, but double quantum coherences cannot be represented as transitions. So they will be present. Okay, So therefore, single quantums are 1, 2, 1, 3, 2, 4, 3, 4. Zero quantum is this. Zero quantum is 2, 3. And double quantum is this. This is double quantum, 1 to 4. So you have these many coherences in your two-spin system. Therefore, what will be the density matrix here? Density matrix is 4 by 4 matrix. The 4 populations along the diagonal and the off-diagonal elements represent the coherences between the states 1 and 2, 1 and 3, 1 and 4. And this is minus I omega 1, 2. That is because we had seen that earlier what it means. This is the complex conjugate of this, or omega 2, 1. If you write, it is the same as minus omega 1, 2. So, and you have these ones. These are the lower half is the complex conjugate on the top. So these are the coherences. You have 4 coherences, single quantum coherences, 1 double quantum coherence, and 1 zero quantum coherence. At equilibrium, all populations are as per Boltzmann distribution, and off-diagonal elements are 0. This we have also seen when we described the equilibrium magnetization. Equilibrium using classical precision. Classical precision. If you remember that, let me draw that once more here for you. This is my B0 field. Then I have this cone here. Spins are precessing around this, and they are distributed all over the cone. This is the same for the lower half also. This is the precision what we described earlier, right? Now, if I take a projection of all of these components on the XY plane here, I will have projections like this, like this, like this, right? And all of these transverse components will cancel because there are so many, there is no phase relationship between this transition and this one or this one or this one. There's no phase relationship. So they can be anywhere in the transverse plane, these components, but the Z component, part of it will cancel by the Z components here, but some portion will remain there. Okay, and that is what is the population. The population difference gives me the Z magnetization, but the transverse components here, they represent the phase coherences between the spins. This is the case of the single quantum. Single quantums is easy to understand this way because these are transitions. These we can measure. The magnetization components are there. Okay, so therefore at equilibrium, I don't have anything in the transverse plane. I don't have anything in transverse plane. What does that mean? So there is no phase coherence between the spins. Therefore, all the off-diagonal elements will be 0 at equilibrium. Okay, single quantum coherences represent transverse magnetizations. Okay, so this is clear. This is a very crucial factor. This is a crucial factor to understand. And here I assume that all of them have the same amplitudes, the coefficients. All these coefficients I wrote earlier, C12, C13, C14, etc. Here I assume that all of them have the same coefficient. This represents the magnitude of the coherence between the two levels. How much is the initial magnetization, initial phase coherence between the spins? So if that were, it can be varying. For different ones, it can be different. That determines how you have created the non-equilibrium state. If all these elements are non-zero, then it means the system is in a non-equilibrium state. Non-equilibrium state can be of two types. One is the populations are not at equilibrium. This is called the non-equilibrium state of the first kind. The second kind will be the coherences there are non-zero. The off-diagonal elements are non-zero. That is called as the non-equilibrium state of the second kind. Two types of non-equilibrium states are possible in general, nothing else. Therefore, the density matrix is a complete representation of the spin system. Whatever is the non-equilibrium state, we can represent it in the form of a density matrix, and we will come across these enormous times in all the multidimensional NMR spectra. Therefore, this is very crucial to appreciate and assimilate this point. Okay. Now, as we have seen, the density operator elements change with the time. They evolve with the time, right? They evolve with the time. So during the course of your experimental sequence, the density matrix keeps changing. Now you can calculate the evolution of the density matrix. So the rho of t changes with the time during the course of the experimental pulse sequence. And what you measure is measure the Y magnetization or the X magnetization or something In the quantum mechanical terms, that is represented as the so-called expectation value. It's called the expectation value, and that represents the measured signal. For example, if I'm measuring the mx magnetization, the x magnetization, this is represented by this kind of a term here. It's called the expectation value, represented by two the arrows here with mx in the middle. But in terms of the mathematics, it is called as the trace of density matrix multiplied by mx. Density matrix and mx. And this is equal to the trace mx rho. What is trace? What is trace? For those of you who do not know what trace is, then let me explain to you. Suppose I have a matrix here and I have the diagonal here. Okay. So let us say this is the n by n matrix. Then the trace is the sum of all the diagonal elements. Let me call this matrix as A. So sum of II. This is the summation of all the diagonal elements is called as the trace. Okay. And what I have to do here? And that represents your measurement, the trace of the product of density matrix with whatever measurement you are doing, whether you are measuring mx or my or whatever you are measuring. Mz anyway you cannot measure, so you measure either the mx or the my or the m plus minus. M plus minus is mx plus imy. M plus minus is mx plus minus imy. So if you are detecting along the x-axis or the y-axis or somewhere in between, then you are actually detecting m plus minus. Assuming that you are doing mx here, so therefore the measurement is indicated by mathematically given as trace rho mx, density matrix multiplied by mx. Remember now that the mx also will have to be represented as a matrix. Okay, now this rho is a matrix and mx also will have to be represented as a matrix. And there is a symmetry here that whether you multiply rho mx or mx rho, it's the same. So far as the trace is concerned. So far as the trace is concerned. And the trace is defined in this manner. Trace A is equal to this. Let us take an example. Take a simple example, one spin system. Simple I is equal to half. There are two levels only. The two levels, I have the population P1, population P2. So I put this on the diagonal, P1 and P2. And the coherence between these two states, I put them as e to the I omega 1 to t and e to the minus I omega 1 to t. The simplest case. Okay. This is my density matrix for this situation. In the sense that I've created a density matrix like this. At equilibrium, of course, these terms would be zero. At equilibrium, there will be only P1 and P2. These terms will not be there at equilibrium. I've created a density matrix of this type. Okay, which means I've created a non-equilibrium state which has off-diagonal elements which are non-zero and they evolve with the time. That is how I get a time dependence here. Rho of t is time dependent because of this. The populations are not evolving with the time, but it is the coherences which are evolving with the time. What is the consequence of this? Now what I do, I calculate the trace. If I calculate the trace, this is my mx. This is the matrix representation of mx. Mx is, in terms of a matrix, is represented by this. Okay, this is 0. And those of you who are familiar with the Pauli spin matrices, this is actually a Pauli spin matrix. 0, 1, 1, 0 is a Pauli spin matrix. Pauli gave these matrix representations of the various angular momentum operators, sigma x, sigma y, sigma z. This is what he gave. But that is ix or mx is half of that, half sigma x, and that is half 0, 1, 1, 0. Now you multiply this with the density matrix. We are taking trace mx rho. And this is my density matrix. You take the matrix multiplication here. Matrix multiplication is what? This into this into this. This gives me the first element. This into this gives me the second element. This into this gives me the third element. And this into this gives me the fourth element. Right? So therefore, I have, when I do this, I get the P1 and the P2 here. And e to the minus I omega 1 to t here, and e to the I omega 1 to t here. What is the trace of this? The trace of this is e to the minus I omega 1 to t plus e to the I omega 1 to t divided by 2. Right? So I'm summing up the diagonal elements. And that is what? That is cosine omega 1 to t. Cosine omega 1 to 2, this is the transition. It is the frequency. Now you include relaxation here. This is cosine omega 1 to t is e to the minus t by t2. This is what we measure, right? So when I measure my magnetization, suppose this is the x-axis, I'm measuring the x magnetization. Suppose I'm measuring the x magnetization. How does it go? I put a detector here. I'm measuring x magnetization. So as a function of time, this is going like this. This is my signal. What I detect here is cosine omega 1 to t. Right? Cosine omega 1 to t, and you multiply by the decay factor. There is the transverse relaxation here, e to the minus, because in this the relaxation was not included. You have to include the relaxation e to the minus t2 by t, and this is my FID. The free induction decay. So simple one spin case, you have one frequency, and it also shows you therefore that the off diagonal elements are actually representing your FID. Phase coherence between the spins, and what you measure in the FID is the phase coherence between the spins, and that too also single quantum. This is omega 1 2 is the single quantum between this. For the single spin, there are two levels. Separation between them is a single quantum frequency. Okay, so now let's go to a two spin system. Two spin system extending to two spins. Now I have the X magnetization of the first spin and the X magnetization of the second spin also. The energy level diagram remains the same. This is already we have seen. And now the density operator, okay, these four states are indicated by this, that is already clear. Now considering a non-equilibrium density operator of the form. Remember, notice this word non-equilibrium density operator. Because the off-diagonal elements are non-zero. Off-diagonal elements are non-zero. I have the populations P1, P2, P3, P4, and all the off-diagonal elements are considered as non-zero. Okay, so now I have to calculate the trace. I want to measure the X magnetization. X magnetization is now the sum of contributions from the spin 1 and spin 2. Okay, so let's try to calculate the trace. So now for the two spins, the X magnetization is represented by this operator. MX operator is this for the two spin case. The density operator remains the same. P1 into that all the off diagonal elements and the P1, P2, P3, P4. Now you do this algebra here. I'm not going to do the algebra there. I showed you the algebra in the case of the first case, one spin case. You do the same algebra here. What do you get? This one, this one, this one, this one. What are these? Single quantum transitions. 1-2 transition, 1-3 transition, 2-4 transition, 3-4 transitions. This is what you see in your FID, except that I have to multiply this all of this by the relaxation. Right? So the coefficients, this is of the individual spins. So therefore, this is the frequency component. So trace, when you are measuring the transverse component of the magnetization in this, and all the superposition of all of these you are measuring. Therefore, this information is contained in the density matrix. No matter what your system is, whether it is equilibrium, non-equilibrium, which things are populated, which are not populated, you will get a full information about this if you understand the density operator, density matrix. So that is where the importance of density matrix comes in. Okay, now you see clearly the off-diagonal elements representing single quantum coherences are selected. This constitutes the frequency component of the free induction decay. That is the detected signal. Notice the double quantum and zero quantum coherences, even though they are present in the density operator, are not detected. They don't show up in your FID. This constitutes non-observable magnetization. Therefore, the single quantum and the double quantum and the zero quantum signals, they don't show up in your FID. Okay. Therefore, detectable magnetization or the observable magnetization directly is always the single quantum. This comes from your direct selection rules from the Einstein transition probability equation. You will see that, okay, it is only delta m is equal to plus minus 1 is what you detect. And double quantum, zero quantums cannot be detected in this. However, their presence can be felt in the density operator. You can manipulate your operations in such a way that you get also this double quantum information. That is how your multiple quantum spectroscopy comes into the picture. I showed you three types of spectra: 2D separation, 2D correlation, and 2D multiple quantum transitions. You create the multiple quantum transitions, but you manifest their effects in the observable single quantum transitions, then you will be able to observe this. And that is the strategy of 2D multiple quantum spectroscopy. Because measured signal is always single quantum frequency. Okay, now the time evolution of the densities. Now I'm considering a very general pulse scheme. So far, we talked about the general nature of the density operator. Now I consider a general pulse scheme. It has n number of pulses, various kinds of perturbations, various kinds of Hamiltonians, and they can be present, and this is the representation of that. So I have here a pulse P1, a pulse P2, pulse P3, pulse P4. It can have any more. In between these, the system is going with the Hamiltonian H1 for a time T1. Here it is going with the Hamiltonian H2 for a time tau 2 or H3, tau 3, and so on. Okay. So now, how do I calculate the evolution of the density operator? I must calculate the density operator. I should know the basic principles how the density operator has to be calculated. Okay. You have to take this word for me that if you know the density operator at time t is equal to 0, at a particular time t is equal to 0, if it is evolving with the time with the Hamiltonian H, this is the Hamiltonian. If it is evolving under the influence of the Hamiltonian as indicated here, it can be different at different times. Then the density operator at time t is equal to t is given by this equation: e to the minus I by h cross ht rho of 0 e to the I by h cross ht. We will not derive this. This comes from the solution of the Liouville equation which I mentioned to you earlier. Similarly, during the pulse also, during the pulse or the effect of the pulse, the density operator also evolves. So how do that calculate? This is the pulse, and this is the inverse of that pulse. Again, has to be represented in some manner. This, you see, this is again complex conjugate here. This is the inverse here, right? This one and this one are the inverse of each other. Minus I by h cross ht e to the I h cross by ht. So this is the same here. Now this is the representation of the pulse. This is also the representation of the pulse, the conjugate of that one. These are the formula for a calculation under the influence of the Hamiltonian and under the influence of the pulse. Okay. Now, if I have a situation like this, how do I calculate? That is indicated here. Start at time t is equal to 0, rho 0. I apply a pulse. Okay, let's go back here. This is my rho is equal to 0. Okay, rho is equal to 0. And then I apply a pulse. So do this P1 and P1 minus 1. Now this whole thing then becomes rho is equal to 0 for the evolution under Hamiltonian 1. Right? So at this point, is the rho is equal to 0 so far as this evolution is concerned. And what is this point here? This point is P1 rho of 0, P1 minus 1. That was that point. Right? Oops, so. And therefore, this portion is the rho of 0 for the evolution under H1 tau 1. And this happens for the period tau 1. Now, from here to here becomes the rho of 0 for the next evolution, for the next pulse, P2 minus 1. Now, then from here to here becomes the rho 0 for the third operation, evolution under the H2 and so on, right? So you start from, so therefore rho of 0 in the beginning starts in the middle and then keep applying the pulses, evolve under the Hamiltonian, again the pulse, again the Hamiltonian, again the pulse, again the Hamiltonian. So keep evolving in this manner. So you keep calculating this evolution of the density operator, and the end, before detection, whatever you have after the detection, and then you have the density operator, and you take the trace with that density operator to see what you are actually measuring. So this is the scheme for generally calculating the density matrix during the course of through the course of the pulse sequence. Such a calculation requires the Hamiltonians as well as the pulses to be represented as matrices. Pulse P is to be treated as a rotation operator. Okay, so typically you must have seen that e to the I theta is a kind of a rotation. And for the pulses, it is generally e to the minus I beta ix. Let's say it's the p something, or it's also represented as r. R of theta, if it's applied along the x-axis, e to the minus I beta ix. Okay, let me use the theta. If the pulse is applied along the x-axis, it is e to the minus I theta ix. Applied on the y-axis, e to the minus I theta iy, and so on. This can be derived. This actually also comes the derivation of the density operator, but we will use this formula. One can do this, but of course, you will see quickly we will change over into avoiding this kind of an explicit calculation. What we will do? This is a simple illustration of how the matrix representations of the pulses will be. This is a 90-degree pulse. Rx pi by 2 is represented by this matrix formula. Ry pi by 2 is represented by this. Rx pi is this matrix. Ry pi is this matrix. Similarly, for two spins, these are the individual matrices for Rx pi by 2, Ry pi by 2, and this is Rx pi, and this is Ry pi. Notice here, in this case, you have a mixture of in minus 1. Okay, and here it is all pure numbers. Here are the complex. These are the complex here. Same thing will happen in the case of Rx. Okay, here there is no this one there. Okay. Now that is so far as the philosophy is concerned. But if you want to do this explicitly for a n-spin system, I think it will take quite an enormous amount of effort and absolutely impossible to do it. It is quite complex and very, very complicated. It will become very time consuming. And then of course, we'll have to find a proper solution. This is what brings us to a new formalism. Calculation using such matrices becomes very cumbersome. So here a new formalism has been developed, and this is called as a product operator formalism. The product operator formalism, to simplify the above calculation, the product operator formalism has been developed for weakly coupled spin system. The density operator is expressed as a linear combination of some basis operators which constitute a complete set. Now, with this density, just to give you the benefit of this, you can do with the product operator formalism simple back of the envelope calculations to evolve the spin system. That is the final result. Okay, but there is a lot of philosophy behind it. So the final result, we will use it, and with the basis operators, it becomes the back of the envelope calculations for the evolution of the density matrix through the pulse sequence. But we will try to understand what this base formalism is. I will try and give you some examples of that. Okay, so let's see. Now for the free evolution, the density operator evolution has to happen. Okay, the density operator is represented in this manner. Summation of various basis operators there. This constitutes the basis set. These are the various basis operators, and summation of these are the coefficients here. And these operators are not time dependent. Remember, these BS are not time dependent. It is the coefficients which are time dependent here. So the coefficient, time dependent coefficient multiplied by the basis operator gives you the density operator, which is a time dependent operator. So now we have to see what are these basis operators, BS. And the BS coefficients actually tell you how much is the contribution of each of these BS. So when you have that sort of a situation, for free evolution, you have to calculate then the evolution of the basis operators. Just as we calculated the evolution of the density operator, now you must know also the free evolution of the basis operators. The basis operators are summation is this, the rho dash is, this is the evolution under the Hamiltonian, and this is the evolution under the pulse. Instead of the rho, I have here the BS. And this is represented by rho dash. This is for the basis operator under the Hamiltonian. Rho double dash is the evolution under the pulse for the basis operator. Right? Because suppose I were to do a operation here, in this one, let us say I were to do an operation P minus 1. I will do the same thing here, right? P P minus 1. You take the P inside, BST, PB minus 1 BS. That's what will become. Okay. So that is what is represented here. The summation BS e to the minus IHT BS for the Hamiltonian evolution, and for the pulse operation you have BS P BS P minus 1. Very simple. This is the way the operation happens. Now the whole calculation is broken down into evolution of a smaller segments, smaller sets of operators. Now, for a basis operator set, what are the basis operator sets? For the Cartesian space, we can represent it in various space. The Cartesian space means we are talking about the XYZ components. This is the Cartesian components. So you have 4 operators. E by 2, this is the unit operator. E is the unit operator of Ix, Iy, Iz. These are the XYZ operator. We talk about Mx, My, Mz. It's the same as Ix, Iy, Iz. For the single one spin case, this is for the single one spin case, there are 4 operators, right? One spin has X, unit operator, Ix, Iy, Iz. This is for the simple one spin. Now for n spins, in a coupled network, there will be 4 to the power n elements in the basis operator sets. For example, for 2 spins, this is written for 2 spins. Each spin has 4 operators, right? 1x, 1y, 1z, 2x, 2y, 2z, and then you have the unit operator E. So therefore, how many total operators are there? You have 1x, 1y, 1z, 2x, 2y, 2z. Then you also have the products. 1x, 2x, 1x, 2y, 1x, 2z, 1y, 2x, 1y, 2y, 1y, 2z, 1z, 2x, 1z, 2y, 1z, 2z. So these are now the complete product basis for the 2 spin case. That's why we call it as a product operator formalism. We have the total density operator will be represented as sum of all of these, sum of these basis operators. These constitute the basis operators for the 2 spin case. So how many are here? You count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, out of these, there are 6 which are 1 spin operators, because 1x, 1y, 1z, 2x, 2y, 2z, these are 1 spin operators. Whereas the bottom ones, the 9 ones, these are 2 spin operators because these are products. 1x, 2x, 1x, 2y, 1x, 2z. These are 2 spin products. Okay, therefore we have 9 of these 2 spin products, 6 of these 1 spin operators, and 1 unit matrix, which is the E. Therefore, the total 16. Okay, now if you go to a 3 spin system, similarly you will have 1 spin operators, which will be 9, 1x, 1y, 1z, 2x, 2y, 2z, 3x, 3y, 3z. So you will have 9 operators there, and similarly you can make a combination of the products. How many products will be there? This will be 27 operators of 2 spin operators, 2 spin products. Okay, A, M, M, Q, A, Q. Okay, A, M, M, Q, A, Q. These are the products, and R is the X, Y, Z. P and R are X, Y, Z. P can take X, Y, Z values. R can also take X, Y, Z values. And A, M, there are 3. Therefore, the total of 27 operators will be there. So for this. And similarly, there can be 3 spin products. These are 3 spin products, A, M, Q. There are 3 spins. And therefore, each one of them has a component P, R, S. P, R, S can also go X, Y, Z. Okay. Therefore, 3 spin operators are also 27. So this will actually give me total of 64. That's what we said. If each one of the spin has 4 operators, as we said, Ix, Iy, Iz, and if there are n spins, there will be total of 4 to the power n. 4 into 4 into 4, 4 into 2, 4 into 4 into 4 into 4. So therefore, depending upon how many spins you have, that many basis operators will be there. Okay, so this is the constitution of the basis operators. Okay, what is next? What do these operators encode? What do these operators represent? First, 1 spin case, you have already seen what they represent. You have Ix is X magnetization, single quantum coherence. That is represented by this. We have already seen the Y magnetization, single quantum coherence that is represented by this operator, minus I here, notice here, and the Z component is represented by this, it has the populations. The Z magnetization is dependent on the population. X and the Y magnetizations are represented by the coherences. That's why you see these are off-diagonal elements. Okay. These are off-diagonal elements. These are, now I am talking this as basis operators. Remember, we are talking about basis operators which are part of the density operator. Therefore, in terms of the density operator, these have off-diagonal elements, diagonal elements. Therefore, the Z magnetization represents populations. Okay, and the X and the Y magnetization represent coherences. And therefore, in the case of single spin, I only have single quantum coherence, X and the Y components. They are distinguished by this one here and minus I here. So this is difficult to see, is it?
No, it's okay.
We can see it?
Yeah, I think they'll be able to see it.
Okay. For two spins, now again I will have, you are taking these two spins K and L. K and L, let's take KX. KX is, you have these four states, alpha K, alpha L, alpha K, beta L, beta K, alpha L, beta K, beta L. So IKX, which are the transitions here? We are talking about the coherences, right? Coherences between the levels. From 1 to 3, which spin is flipping? Is the K spin. Therefore, 1, 3 is the K spin transition. 2, 4 is also K spin transition. Okay. So in terms of this final spectrum, what we will see, if I want to represent that in terms of this spectrum, this represents the 1, 3 and the 2, 4 transitions. Okay. So this is the K magnetization, X magnetization of the K in phase with respect to L. And these two have the same sign, you see. These two have the same sign. Therefore, we call it as in phase. In phase magnetization of the K spin, and this is X magnetization because this operator is IKX. Now, similarly for the L spin, this is L spin. What are the transitions? The transition is 1, 2 and 3, 4. 1, 2 and 3, 4 are the L spin transitions. Okay. And therefore, these ones in the spectrum are 1, 2 and 3, 4. And what does this represent? X magnetization of L spin in phase with respect to K. Why I am saying with respect to K, you will see that very soon. In phase, these two transitions have the same sign, and therefore we call them as in phase. Let's look at KY. Now KY is the same as this, except this is the Y component. Y component, that was the X component. If the Y component and the X component will have to have opposite phase, they cannot have the same phase. If Y is in phase, Y is absorptive, X is dispersive. If X is absorptive, Y is dispersive. Therefore, these two transitions are now dispersive signals. IKY represents, if IKX represents absorptive signals, IKY represents dispersive signals for the same transitions. Okay. And similarly, ILY represents the dispersive signals of the L spin. 1, 2, 3, 4. 1, 2, 3, 4, these are absorptive and these are dispersive. Y magnetization of L in phase with respect to K. This is how the spectrum will look like. If I have a term called ILY in my density operator, I will get this sort of a spectrum. If I have a term called KY, I will get this sort of a spectrum. Okay. And IKX, if I have, I will get this spectrum. If ILX I have, I get this spectrum. Now suppose in my density operator has this term, because remember the density operator is a summation of all the basis operators. So therefore, all of these can be part of your density operator. They can be summing up, contributing to your density operator. Suppose I have a term which is like, this is the two spin product, IKX, ILZ. What is this? This is the X magnetization because the transverse component is K, IKX. IKX is transverse magnetization. Okay, whatever is X or Y represents a transverse component, the transverse magnetization. But this LZ means it is the transitions will appear like this. 1, 3 and the 2, 4 have opposite signs. So if 1, 3 is positive, 2, 4 is negative. That is what is called as antiphase. So this is X magnetization of the K spin anti-phase with respect to spin L. Okay, now it is clear when you say here, this is in phase with respect to L. Here when it is Lz is present, it is anti-phase with respect to L. So if I have such a kind of a term in my density operator, I get the spectrum which is like this. 1, 3 is positive, 2, 4 is negative. Now similarly, if I have 2 IKY ILZ, I will have these two transitions 1, 3 and 2, 4. But now if 2, 4 is positive, 1, 3 will be negative. How do I represent this? So these are the dispersive signals. So this going up and then down, and this is if they call it as positive, the negative one will be, first part will be negative, then the second part will be positive. Okay, so these have opposite signs. If I call this as positive, this is negative. Okay, whatever this. So in this is how the dispersive signals will appear. And in this case, you see these are both positive, positive. Right? Dispersive signals in phase. So here again positive, positive. These are all positive, 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 positive. And this is negative, positive. Therefore, these two terms, therefore the two spin products represent antiphase magnetizations. Y magnetization of the K spin antiphase with respect to L gives you dispersive antiphase components. 2 IKX ILZ gives you the absorptive antiphase components of the K spin. Okay. Now take the 3-spin case. That was the 2-spin case. Now in the 3-spin case, what will have? Each one of them will have 4 transitions, right? 4 transitions. There are 3-spin energy level diagram here. So you can see the transitions, various transitions there. So you have here K spin, M spin, and L spin. And the energy levels are described here 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now the transitions 1, 2, 3, 4, 5, 6, 7, 8, these correspond to one spin. And what is that spin? That spin is the L spin. Okay. 1, 2, 3, 4, 5, 6, 7, 8, all the red ones. Right? 5, 6, these are all the L spin because the L spin is flipping. Alpha L to beta L, other two are remaining the same. And similarly, 2, 4, 1, 3, 6, 8, 5, 7. 2, 4, 1, 3, it is this one. 2, 4, 1, 3, 6, 8, 5, 7. These belong to the K spin. So there is the K spin which is flipping there, right? K spin, this goes alpha K to beta K. Other things are the same. And now the blue one, which is 4, 8 and 1, 5, 3, 7 and 2 to 6. These 4 ones there. 4, 8, 1, 5, 2, 6, 3, 7. These are the 4 transitions of the M spin. And here I have shown all of them as in phase. When I say in phase, I show them all in the same direction. Going like this, going like this. Okay, all of them are going in the same direction. You remember what I showed in the previous case, in the 2-spin case. If they are going in the opposite direction, then they represent antiphase. They go in the same direction, they represent the in phase. So when you have an energy level diagram like this, then you have the in phase magnetization of all the 3 spins, and therefore you generate a 3 quartets there. Therefore, we term this as this is X magnetization of a L spin in phase with respect to K and M. So I will call this as X magnetization of the K spin in phase with respect to L and M. Similarly, this one is the X magnetization of the M spin in phase with respect to K and L. So all of these are in phase magnetizations, and they are represented in the energy level diagram with arrows going in the same direction. Or in other words, absorptive signals. If I go in the same direction, say absorptive signal. If I put in the opposite direction, it is emissive signal. Emissive signal means negative direction. You have to put that in the negative direction. Okay. Now I've shown you here some of those situations. So this one here, what we have considered is one of the two spin product I have taken. In the case of three spins, we have two single spin operators, two spin operators, and three spin operators. Okay, three spin products. I consider one two spin operator here and one three spin operator. Consider the two spin operator here. This is the 2 IKX ILZ. So what this should represent to me? This should represent X micronization of the K spin antiphase with respect to L spin. Okay. So the K spin magnetizations are the green ones. 1, 3, 2, 4 and 5, 7, 6, 8. Notice here now, these two I put it in opposite directions. One is absorptive, other one is emissive. This comes down. Similarly, this is absorptive and this is emissive, comes down. Now, if I represent the 1, 3 as positive, the 2, 4 will be negative. 2, 4 will be negative. And 5, 7 will be positive, 6, 8 will be negative. So therefore, among these four lines, you will see two lines will be positive, two lines will be negative. Okay, so 1, 3, 2, 4 have opposite phase and 5, 7, 6, 8 have opposite phase. So this is the result of a two spin product. Two spin product, and the M spin is not coming into the picture here. It remains the same. It's not coming into the picture. Now consider, similarly you can draw for 2 IKY, ILZ, okay, and ILX, IKZ and things like that. For every operator you can do this. I've illustrated this with one of them, IKX, ILZ. Consider a 3-spin operator. The 3-spin operator, let's consider this 4 IKX, ILZ, IMZ. Okay. So what does this mean? This is the X micronization of the K spin. X micronization of this K spin, it is antiphase with respect to L as well as M. Okay. So this much portion was of the K and this much portion was, let us say, belonging to the situation with respect to the L spin. Now what happens here? Now you see this remains the same, but now this becomes opposite to this. 6, 8 goes up, 5, 7 comes down. This is what we say, this magnetization is antiphase with respect to both L and M. And schematically you can see here, if I draw this 1 to 3 is positive, 2 to 4 is negative, same as this. Now, this now 5, 7 becomes negative. The 5, 7 was positive here, 5, 7 was positive here. The 5, 7 becomes negative, 6, 8 becomes positive. Which one is it? Here. 6, 8 becomes positive. So therefore, this is considered doubly antiphase. The X micronization of the K spin, it is doubly antiphase with respect to L and M. So similarly, you can write for all the products, various products, you can write this kind of a situation, and that is a whole list of the product spin products, and you will see what is the relation of those with respect to the spectrum. What you will observe in the spectrum. If any of these components are present in your spectrum, you will see what is the observation. You can also see from here, what are these observable operators? Suppose I were to consider the total integral of this, it will be 0. If I take the total integral of this, it will be 0. Right? And this is what we say when we say that these terms are not explicitly observable, because the total integral of that is 0. If I were to take a trace of mx with this, then it will come to 0. If I take the trace of this with kx, it will come to 0. What happened? The block, yeah.
Yes, right.
Okay, it will go to 0. Therefore, it is only the in-phase magnetizations which can actually measure. The integral of all of those will be non-zero. The integrals of these antiphase magnetizations will all be 0. Okay, so therefore let me write here integrals of antiphase components will be 0. So these terms are, these are non-observable. So they will eventually evolve in terms during the T2 period of our measurement into observable magnetization. Then you will see. Ultimately, when you do that, then they will appear in this format, this sort of a spectral features. Okay, now this is a summary of all of that. I illustrated this to you with some of those and to show which ones are observable, which ones are not observable, and this is the summary of all of those. This you'll have to remember and by heart it. Okay, that is the kind of a thing which is the summary of the product operators here. IZ operator represents the populations in the Z magnetization. IX and IY operators in a multi-spin system represent in phase single quantum coherences along the X and the Y axis respectively. 2 IKX, IN, 2 IKY, ILZ represent single quantum coherences of K spin antiphase with respect to L along the X and the Y axis respectively. Similar interpretations hold good for the L spin single quantum coherences. This I did not explain to you because this cannot be explained by vector pictures or drawing transitions. 2 IKX, ILY, such products are also there where you have two transverse components. IKX, ILY, true transverse components. 2 IKY, ILX, true transverse components. 2 IKX, ILX, 2 IKY, ILY represent mixtures of double quantum and zero quantum coherences, and suitable combinations of these represent pure double quantum and single quantum coherences. And that combinations are indicated here. 2 IKX ILX plus 2 IKY ILY represents X component of zero quantum coherence. 2 IKX ILY minus 2 IKY ILX represents Y component of zero quantum coherence. 2 IKX ILX minus 2 IKY ILY represents X component of double quantum coherence. And 2 IKX ILY plus 2 IKY ILX represents Y component of double quantum coherence. And the final 2 IKZ ILZ represents two spin ZZ order. These ones are responsible for various kinds of transformations that will happen when we actually do density operator calculations. All of these terms will come into the picture and we'll have to see which ones are observable, which are not. Remember, these ones are not observable directly because these are not according to the Einstein transition probability. Single quantum only is observable, double quantum and zero quantum are not observable. I actually showed this to you in the case of a two-spin system. Explicit calculation of the density operator showed you that although they are present, they don't show up in your FID. Okay, but you have to devise other methods to get the information about this as to modulate your observable single quantum coherence. That's what will happen. This is what will happen in all various kinds of multiple quantum experiments and in other correlation experiments also. So this is the basic principle, the fundamentals of product operator formalism. I think we'll stop here. Yeah, it's quite heavy, but I think it is.
Yeah, I think let them see it.
Let them
see
go through the presentation because it is available.
Yeah, it's available.
They can
Yeah,
relook into it and then find out.
correct.
And if any questions,
the next lecture post कर दो. Lecture दोनों lecture को ना.
so sir, this PDF file, this reading material,
PDF file.
हाँ ये लोग
You can make a PDF file.
वो PDF भी करता है.
करके तुम लोड
इसको PDF करके लोड कर.
लास्ट
वो PDF करके लोड करता है.
इसको PDF कर दो, PDF करके वो रीडिंग मटेरियल में डाल दो. Let them go through it once again.
Yeah,
This is really heavy for them.
this is heavy.
Mathematics थोड़ा देखना पड़ेगा.
So they have to go through it.
This matrix ना
Yeah.
or this aim ना.
Yeah,
So it means how you're deriving like for let us say this for two spin system na image matrix na you are putting na the I think you are putting 0
0 1 1 1 0 0 1.
right. So how
See, what you have to do, you take the operator, MX operator, and you calculate the matrix elements. On both sides you put, you have the alpha, 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 beta, beta, alpha, beta, beta.
okay.
And calculate the matrix elements.
Okay.
In the middle you put this operator. What is the value of multiple explicit calculation you can do? MX is M1X plus M2X.
Okay.
Okay, and on the matrix elements you put alpha, 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 that is 1, 1. Alpha, 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 beta is 1, 2. Alpha, 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 theta is 1, 3. Like that you can calculate explicitly. There is another simple method of doing it, and that is to take the direct products. You take if you take 0, 1, 1, 0, 1, 1, 0, take a direct, I will show you that next. So the 0, 1, 1, 0, take a direct product 0, 1, 1, 0.
Sir, you
So
can
what-
also do it on the screen. You can also do it on the screen.
On this screen.
This screen.
some hai over sab log? You can see, so what this is direct product means it will become 4 by 4 now.
Yes.
2 by 2 into 2 by 2 becomes 4
Ask
by
them
4.
if they need questions.
So what does it mean? Wherever there is one, you put the whole matrix. So this will become 0, 0. Okay? Sorry, 0, 0 multiply with 0, 0. And then we multiply with this 0, 1, 1, 0. And this you are multiplying. So this one you multiply 0, 0, 1, 1, 0. This one again 0, 1, 1, 0, 0, 0.
Spell it out. Or ask anything.
This was single half. So this is what became for IX direct product. I1X plus I2. No, this one actually is I1X into I2X. Okay, this is not the two-spin case of, this is product of I1X into I2X representation. This is. Now to calculate the I1X plus I2X, if you want to do this, these are individually present. So you will have to write this 4 states, alpha, alpha, this I1X plus I2X, alpha, alpha, this is your product 1, this is A11, okay, it's 1. So A12 will be alpha, alpha, plus the same operators here, and this is alpha, beta, A13, alpha, alpha, beta, alpha. So like that, you have to explicitly calculate for all of those.
Okay.
So when you do that, this is the direct product is for the I1X, I2X calculation. See, now notice here now, when you do this, what you got here? You got the zero quantum coherence, double quantum plus zero quantum. This is what I said in that
Right.
this two spin products will actually indicate to you mixture of double quantum and zero quantum. Individual one which you want to calculate, you have to put it
Yeah, right,
in this
right.
manner.
So then these diagonal things will,
Yeah,
so here the diagonal things are not there.
not there.
It is only
It only has zero quantum and double quantum.
Mm.
When you do this, you will get 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. This is what we will get when you explicitly do this calculation.
Thank you, sir. I think your book is having all these
It
things.
has all of those. It has all of those.
So, students, is there any doubt? Anyone is asked anything? Okay, sir, then you can say it's done. So
It's
next,
clear? Yeah,
So next class,
next class will be Wednesday, no? Yeah.
yeah. So you can do the same thing with direct product if you want to do. You can do for I1X, I2Y also. You can do I1X, I2Y, whatever one you want to do, you can do that in direct products.
Okay, sir.
Okay.
Then student.
Okay, thank you all. We'll join on next Wednesday, same time at 4 o'clock.
Yeah, so we'll continue with some of those.